So the weak form, in general, we only did the weak form for Poisson's equation, but there are also weak forms for many other equations. So in general, the weak form contains two elements. One element is what's called the bilinear form. We write it as A of U and V. So an example of the bilinear form we have before is minus integration of a and a to b, the derivative of x times the derivative of v. It is equal to, so this is the bilinear form. It has to satisfy a certain number of criterion. First of all, a times any C1 times U1 plus C2 times U2 V has to be equal to C1 times A of U1 V plus C2 times U2 V. So this is simply a linearity in the first argument. It also has to satisfy a similar linearity in the second argument. Is equal to C1 times A of U V1 plus C2, there is A here, A, U, and V2, right? So this is the standard definition of what is linear. And the reason it's called bilinear is that because it is linear with respect to both its arguments. In this example, it's pretty clear why each of them are linear. If you perform linear combination of u, you can pull these linear combination coefficients out of the integral. Alternatively, if you perform any linear combination of v, you can also pull these linear combination coefficients out of the integral. And in our example, this bilinear form has a particularly nice property. It's symmetric. Right, so if you exchange u and v in these two arguments, the value doesn't change. And this, as if you remember, has intimate relationship with the symmetry of the matrix A we got out of discretizing using finite element. Okay, but like for other equations, for example, if we have odd derivatives in the equation in the differential equation, then the bilinear form we're going to get is no longer going to be symmetric. Okay, the other element we need in the defining the weak form is a linear functional. We call it L of V. So L of V, in our previous example, we have this integration of f times v dx is equal to our L of V. So L of V has a single argument because f is predefined. F is a known function, is a given known function. So another example of a linear functional is L of V simply equal to V at 0.5, right? Our previous example of like when f is a delta function. So that's also a linear functional. The linear functional has to satisfy a very similar criterion as the bilinear form. It has to satisfy L of C1 V1 plus C2 V2 has to equal to C1 times L of V1 plus C2 L of V2. That's why it's called a linear functional. Now, once we define the bilinear form and the linear functional, the weak form also requires a space. So actually, bilinear form and linear functional, they both require a certain space. So u and v are in a certain space, and this is v in a certain linear space. I mean, they should have a in the simplest form of finite element, the u and v should be in the same space. Then we've got what's called a Galerkin method. And in more advanced treatments, U and V can belong to different linear spaces. But no matter what you do, the V in the bilinear form and the L in the linear functional has to be in the same linear space. So the weak form is to find U within X. So let's actually make it clear, make it more general by saying that U is in a certain XU, this is in XV, this is in XV. So find U in XU such that A UV plus L of V equal to 0 for any V in this space XV. And a special case is it's XU is equal to XV. That's called the Galerkin method. Galerkin method also requires the space of XU and XV to be the same, and we are also discretizing XU and XV in the same way. When we go from this infinite dimensional space to a finite dimensional space, we are also selecting the basis also in the same way. All right. So this is a general form of a weak form of differential equation. And for a lot of differential equations out there, we can find this kind of weak forms that represent the differential equation but gives more general solutions, even if the right-hand side of the differential equation or some coefficients in the differential equation is no longer well-defined functions. Okay, an example I can give is the following. An example I can give is in structural mechanics, people often solve some kind of equations for structural elements like a beam. And the simplest form of basically all the beam equations involves fourth order derivatives, but the simplest beam equation, the Euler beam equation, has a form like that. So the fourth order derivative of the solution plus f is equal to 0. And here U describes the bending of a beam, and F is the loading on the beam. So F and U is the F is loading, U is deflection. All right. So, and we can derive the weak form again by multiplying a test function U on this equation. So let's say this is A, this is B, dx is equal to 0. And because U involves a fourth order derivative, we need more comprehensive boundary conditions than what we have for the Poisson's equation. So the boundary condition for the beam can be simple support, can be clamped. A simple support means the value of U has to be a certain value, which means the position has to be fixed. And also it has no bending moments, which means the second order derivative of U has to be 0. I mean, second order derivative is like the curvature. Or it can be clamped, which means the first and the U and the first order derivative has to be 0, which means like the slope has to be fixed. So let's for example give use the example of U and U derivative both equal to 0 at 0 and 1, or at A and B. Then during the integration by parts, okay, so if we have this, of course, when we define a ux also has to satisfy these boundary conditions. Okay, and then what is ux? Ux is going to be so xu is actually the Sobolev space in between A and B of 2, because in this case u is taking a fourth order derivative, and when we derive the Sobolev space, we're going to find out that although we won't require that the solution and the test function to have a fourth order derivative, but they need to have a second order derivative. Okay, so what we're going to get over here is that we integrate by parts once, so a and b, v of fourth derivative of x. If we integrate by parts once, we get a minus sign, we get a derivative of v, and we get a third order derivative of u. And we integrate by parts twice, the negative sign is gone again, and we have a second order derivative of v and a second order derivative of u. So that's going to be our bilinear form. Our bilinear form is, instead of in the Poisson's equation, a product of the first order derivatives, the bilinear form in the beam equation, in the Euler beam equation, is a product of the second order derivatives of the solution and the test function. And what is our linear functional? It's going to be the same, right? Integration of v and f. So that completes our derivation of the weak form. So the ingredients of the weak form, first of all, we need to define the space of the solution and the test function. In this case, both can be H2. We also need to define a bilinear form. In this case, the product of the second derivatives. We need to define a linear functional. In this case, the product of the test function v with the known function f. Okay, and we can use finite elements to solve this. We can construct a in this case, we're going to notice that piecewise linear function doesn't work anymore because piecewise linear functions are not in H2, right? So we need to derive some kind of a piecewise quadratic function. And we're going to use the piecewise quadratic functions to construct the matrix Aij and construct the Bj by evaluating these bilinear form and linear functionals on the basis functions. And then we are going to solve the same matrix equation AU equal to B to get the linear combination coefficients of these piecewise quadratic basis functions. And then the solution has to be reconstructed using the linear combination coefficients on these piecewise quadratic basis functions. All right. So this is just another example of what the weak form can be for other equations.